everybody, how's it going? My name's Mike. I run a small independent game studio in Berlin where we make games that sort of are designed for people who don't normally play games and use non-traditional interfaces to connect them to each other and the world around them. But I'm here to talk to you today about my practice specifically making games using React and Redux, and even more specifically making local multiplayer games using them. So games where every person has their own device that are networked together, but you're in the same physical space talking to each other. So this talk is going to be sort of two parts. First, I'm going to talk a bit about using React and sort of more from a design standpoint, what does it mean to make games using React? Why would you? What sorts of games should you make? And then we're going to get a little technical into the nuts and bolts of doing networking. Sort of an overview, a lot of classic games netcode problems, but specifically through this lens of, so we're using React and Redux or some Flux-like architecture. How does that work? But before we get into that and talk about React or even JavaScript, I want to talk about what we should be thinking about when we decide to make a game or anything with some sort of technical tool. Because any sort of tool you use is going to shape the sorts of things you can make with it. And that sort of constraint can breed creativity if you approach things from the right way. So if you know you want to make a game, if you wanted to make a game like Tetris or Mario Brothers, you could write it in React. You could also write it in a traditional game engine like Unity or Unreal. You could write it in assembly. You could open up a copy of Minecraft and get some redstone and get a computer going there and implement Tetris in Minecraft. What do you actually gain from using React other than, obviously you like React, React is wonderful, I'm standing here at a React conference. But that's not a particularly good answer. And like specifically, I think in this example, you don't really want to make Super Mario Brothers in React. Like you totally could. Like let's think about what we need. You need a physics engine. You need sort of continuous input. So if you're holding down the button, you're going to add acceleration to your character that's going to update velocity, that's going to update your position. Every frame, you probably have some core update loop to manage this. There are some reasonable patterns for figuring out how you duct tape this like very standard game design architectural pattern of having a core update loop that runs 60 times a second and bolting that onto React's sort of more event-driven model. But you could also just use Unity, and that would work really well. Which brings us back to designing within constraints. That is the opposite way of that. That is saying, I have a game that I want to make. Let's solve some hard engineering problems through brute force in order to make it happen. What happens if you go from the other way? So I mentioned a few seconds ago that I generally make games that use non-traditional interfaces. What does that actually mean? As mentioned also a few minutes ago, this is a game called Hello Operator. This is a game that's played on a physical telephone switchboard from 1927. Players sit down and learn how to use this as if it was their day job in the 1920s. And it was sort of an important design constraint from the beginning that I wanted this to be playable by people like who could sit down and read the original instruction manual from the 20s and know how to play it. Which shaped a lot of the design decisions when we had this physical hardware that works a certain way. There is a computer running JavaScript inside it, but it is running through original 1920s wiring. That shapes the scope of what I can make. This is a piece called Computational Flâneur, which is a generative site-specific poetry walk for Fort Mason in San Francisco. So as you wander around this physical park with your phone in your pocket and your headphones on, a robot makes up poems for you based on where you walk. So you walk by the waterfront, you hear poems of the sea. You walk by the cannons, you hear poems of war. Sitting down and thinking about what is a poetry generator that makes poems based on a physical space is one thing, but it had to be deeply influenced by the actual nuts and bolts of how GPS works. GPS is only so accurate, which means I only know to a certain level of fidelity where you are and how often I can change things based on where you are. So even though there was all of this sort of creative aesthetic work of how should this neural net generated poetry sound, it was influenced by the technical constraints of how do these satellites in space talk to your phone and tell it where you are in the world. As a third example, since those are sort of both pretty out there, like even specifically talking about networked video games, this is a game called Space Team that I did not make. You can download it for free for Android and iOS, and it's delightful, where all of you and all of your friends are piloting a spaceship that is falling apart, it seems, but you have to somehow pilot this ship without dying. And your interface to this game is this sort of set of knobs and dials with all of these techno-babbly inputs, and you have a set of instructions like set shift sanitizer to 1, but you probably don't have the shift sanitizer on your device, so you have to yell at your friends and get someone else to do it. So this is a game where the pure joy comes from yelling at your friends, which is delightful, but it's also really, really smart, because the thing is, local networking in a peer-to-peer ad hoc fashion across smartphones is an unsolved problem for the level of quality you would want. Doubly so if you have iOS devices trying to talk to Android devices. Bluetooth is pretty broken across devices, across iOS and Android. Wi-Fi has its own problems. So this is a game that has a lot of network connectivity problems. But if you think about it, this is a game where a packet now making through means it's not going to recognize that you pressed a button, which means your friend who yelled at you to press the button is going to yell at you even more. So this is a game that takes the core joy of the game, and network connectivity failure causes you to experience that more often. That is really smart. Which brings us all the way back to React. Like, again, I don't think I need to talk about why make games in React. Like, if you want to make games, you probably want to use the tools that you already have in your tool belt. We'll talk a little bit about the what, but I think the how is the more interesting question. Or sorry, the other way around. Like, we'll talk a little about how, but the what and what sort of games you should make is interesting. Like, what sorts of games are afforded by React as a tool? What sorts of things does React make it easier to make that other like traditional game engines won't? So I'm going to talk about a prototype project that I did instead of speaking in the abstract. This is a prototype called Word Temple. The idea is that it would be a dungeon crawler that is also real-time collaborative Scrabble. Obviously, what else would you make? So you have this procedurally generated dungeon that has a whole bunch of rooms, and you're moving from room to room, collecting treasure and trying to escape. Each of these rooms is a small 7x7 word grid, like in Scrabble or Words with Friends. And you have entrances and exits to these rooms that you have to place tiles to play words to form a path between different entrances so you can move from room to room. You might also encounter a puzzle like, this door is locked. If you want to unlock this door, here's a tile on the grid, play a word over it that's an animal. So I'm not going to get too deep into how this is implemented. You can sort of imagine this is a pretty straightforward hello world level React app. You have some state representing a bunch of rooms. Each room has some entrances and exits, maybe some place tiles. You have a tile rack. We have a tile bag that we're drawing tiles from, using React drag and drop to handle drag and drop across mobile and desktop. And there's sort of a series of actions around you're mostly moving tiles around, whether from your tile rack to the board or moving things on the board or swapping orders. Pretty straightforward stuff. But the thing is, this is fundamentally a slow UI-driven game, which makes it really, really perfect for something like React. So what do I mean by that? It's slow, like this is a real-time game that you can play pretty quickly, but on the time scale of computers, it's pretty slow. If you're a competitive Street Fighter player, when you press a button, you care that it executes the punch or kick or whatever in the exact same frame that you intended it to, where a frame is once every 60 seconds, so that's 19 milliseconds. 19 milliseconds is pretty fast. Whereas here, even if you're a robot when it comes to knowing what tiles you should play, the act of you physically dragging tiles around, you can probably do a tile or two per second, I don't know, which means we don't have to worry about the question of the haters going, well, React's not fast enough, what about performance? For anything we're going to do, like we're solving the same class of problems that people building web apps are solving, so we don't have to think about performance, really, for the most part. And similarly, sort of this is a UI-driven game, by which the sorts of interactions you are doing are the same sorts of things that like desktop GUI interface paradigms are built on, that web browsers are built on, that tools like React are made to build. There is sort of increasingly this huge trend of sort of interface-driven games, where you have these games that look like various computer systems. So as you play them, you're interacting with a fake desktop or a fake smartphone, or in the case of Papers, Please on the left there, a fake physical desktop where you're moving papers around. But the metaphors fundamentally map to the things that we are building as web developers rather than these sorts of interactive simulationist worlds that a lot of games are, which is great. But also, like, even though this specific game, like I guess there's the metaphor of placing Scrabble tiles, it is not like, I assume most of you don't regularly play Scrabble on your computer. But still, like the way it is built, like this is not a virtual world where the way we're rendering it, we have to think really hard about, you know, does the aspect ratio matter? Like, no, we have a set of components that represent a board and a tile rack, and we can very easily style these using CSS by positioning things on a grid and write some media queries to have the same design scale up and down to desktop to phone to wherever. But so that is it as a single player game. As I mentioned, this is actually multiplayer though, where the idea is I can join, I can play the game on my phone or on my computer, and it works great. If someone else joins the exact same game, they are living in the same persistent dungeon as I am. If I go to a room where they have been, I can see what tiles they've placed. More crucially, if we are in the same room at the same time, when they place a tile, I can immediately see it, which is where it gets a little tricky. So let's think about the simplest possible way we could build that out. So in the current state, this sort of very, very simple, like Reduxy app, where when I drag a tile onto the board, I'm going to dispatch presumably some play tile action. Maybe it has an array, an index into my hand, and maybe XY coordinate of where it's going on the current board. As a result, it's going to place that tile on the board. It's going to remove the tile from my hand. It's going to draw a new tile from the tile bag and put that in my tile rack. That's pretty straightforward. If we have two clients, you can imagine maybe we just take that action and we take that JSON payload of that action and send it over the network as some sort of RPC. And then the other client's reducer can process that same action. So if you have Alice on the left and Bob on the right, Alice placing a tile, Bob's game also gets that Alice played a tile action. In my specific case, in this prototype, I was using Redux Thunk, but it really doesn't matter. You could use whatever your preferred choice of doing asynchronous actions is. This sounds great. This falls apart pretty quickly. So imagine Alice and Bob both place a tile in the same place at the same time. From Alice's standpoint, she's going to place that W, and then she's going to get the action that says Bob played an A, and that's going to override the W, and the result is the game is going to have an A. Bob's is going to go the other way around and is going to play the A and then the W, and then you have two people whose games disagree about what the state of the world is. There are a lot of solutions to this. Practically, if we wanted to sit down and say, what is the best way to solve this, CRDTs, conflictly replicated data types, are probably the strongest choice. Talking about implementing those is its whole and other talk, and probably drives out a lot of complicated changes to like the data structures and how this is actually implemented. But without that, sort of all of the other approaches we have, we are now deep in the mire of consensus algorithms and distributed systems and things that are way outside my pay grade. Doubly so given that this isn't distributed systems from the standpoint of a bunch of servers that we control. This is a bunch of arbitrary web browsers that users have, and we care about latency on the order of tens of milliseconds, which is really hard mode for distributed systems problems. So let's see how we can forget this problem entirely. So instead of arguing over what the state of the world is, a naive simple next approach is to say, all right, what if we have some device that is the arbiter of what is real and what is happening? Since this is all JavaScript and we have our reducer as a nice pure function, let's say we have a node server that runs that reducer. And anytime anyone performs an action, they're both going to reduce that action locally. They're also going to send it to this node server. The node server is going to figure out the new state, and it's going to broadcast to all connected clients, hey, there's a new state. You should completely override your store with that state. So doing the action locally means we can have nice snappy feedback. So as soon as I play a tile, it shows up. But by overriding the state, that means that everyone can agree, we know this is what the state of the world is. It means we'll have that consistency on the time frame of whatever our round trip latency is. This isn't perfect. Like sending the entire game state anytime anything updates might eventually fall down. For a game this small, it works really well because it means we don't have to think about how are we sending patches, like are we going to run into out of sync issues with however we're sending those nuanced diffs. But for now it works, that's great. We also need to be careful that if someone's dragging and dropping and a new action comes in, make sure our UI programming is robust enough that we're not going to clobber that. We also need to think about things like seeded random number generators. So if I'm placing a tile and drawing a new tile from the tile bag, the tile that I'm getting needs to be the same one the server sends a second later, which also then means, well, is sending the random number generator seed a security flaw? If this was a for money poker game, that might be a problem. This is a collaborative game that you play in friends with your person, so that's not really our security threat model, but it's still a problem. So in general, this broadly works. Just so you can see that it works, I think this is really, let's see if I can get this computer working. Whoa, that's big. So it's also impossible for me to control this like this. So what we're going to do is try to control it from my phone. Good. game. Hey, great, that works. And I think if we refresh this as well, yeah. So you can see in real time, it's updating as I'm dragging stuff around. It's validating that words are valid. Yeah, this is less exciting since you can't actually see how fast it is. But also, crucially, this is cheating because the game works. But it works because there is a computer that is sitting right here that is running both the server and 2 of the 3 game clients, and it is running on a wireless network that is broadcast by the 3rd client. So how does latency actually work? Like anything, we want to measure it, but even that opens up a whole bunch of questions of, well, how are we actually doing this? Like right now, we're assuming there's a node server that we're running, but there are a whole bunch of options. We talked about how we don't want every client to have its own sense of what is true and to have them debate about the true state of the world. But instead of being a dedicated server, it could be one of the clients that we've defined as the host. If we do that, are we worried about, like, is it going to work great on a MacBook, but not great if it's a very old phone? I don't know. We also have transmitting data to worry about. In this case, everything is running over WebSockets, which work great because it's super easy. Every browser supports them. If the sort of quote-unquote host is a client, maybe we could use WebRTC for peer-to-peer connections. Not really going to talk about that because WebRTC is hugely complicated. There's a lot of handshaking required to get a peer-to-peer data connection up and running. It's in theory really great because it means we have UDP-based connections. Sort of games tend to favor UDP connections over TCP pretty heavily because in games, like in this case in particular, we're sending a game state object every time it changes. We don't care about ensuring delivery order. If a packet doesn't get delivered, we don't care. We just want the latest state of the world. And TCP is going to ensure that order that we really don't care about. So WebRTC being UDP-based is hugely beneficial, and it's sort of a large problem for browser games that there isn't a very well-supported UDP transfer mechanism. But like, I've seen a lot of friends use WebRTC for hello world level examples and sort of run into difficulty scaling it up. Also, I don't believe it's currently supported in iOS mobile Safari, which for me makes it a complete non-starter. But so WebSockets are great, but that means that we then need a bouncing server. So even if it is theoretically peer-to-peer, we still need a server somewhere that exists to send WebSocket messages between clients. Also, this physical server, like maybe it's running on my computer, maybe it's running on a VPS slice, like on EC2 or DigitalOcean or something. Maybe we've pushed it to Heroku. Maybe we're even using something like Firebase where we're just giving it some JavaScript and telling it to figure out how to run. So for the purposes of testing, because it's easy to talk about latency, you need to actually measure it. I just threw together this really simple app, just using create racked app and Redux Thunk. All it does is the client knows how to send a ping that includes a current timestamp. Any of the servers that receive it just immediately send back a pong, and then the client can take the current time and do some time math and figure out how long that round trip took, making sure that's happening on the same client so we don't have to worry about synchronizing clocks or anything like that. Which is really interesting because this raises a question about what is latency. This is going to tell us what is the complete network round trip of something. That's also including the overhead of running various levels of JavaScript on both the client and the server. But it's also not including things like how long does it take from when I touch the screen to actually register a button press. There's this guy named Dan Liu who does a lot of amazing blogging around many things, but specifically he's done a bunch of blog posts around measuring latency. And I think the proper way to measure this really would be something like he does, where we'd have a video camera running at 240 frames per second or whatever and actually measure, well, how long until I physically touch the screen until I see a response. But this is good enough. We can compare relative network strategies. So I made this little test grid. We have is the thing that is executing the game logic a browser-based client, or is it a server? Is it running locally? Is it on Heroku, or is it on Firebase? If it's locally or on Heroku, it's going to be the same node app that's running a WebSocket bouncer. If it's on Firebase, it's a little wonkier. I'm using their real-time database as a transfer mechanism, which is not how they intend you to use it. There's sort of a document in their NoSQL database that represents the game state. JavaScript clients can register to that and get a callback anytime it changes. We have another document that we're essentially using as a message bus, so they can just shove their actions into that folder, and whatever is acting as the reducer can subscribe to that and sort of pop those off the queue and then modify the state, which could either be a client, or it can be their Firebase Cloud Functions, which is their like AWS Lambda-like serverless JavaScript. This is all very silly, but you might be surprised to know that is not as unperformant as you might imagine. So these numbers aren't that interesting. The couple interesting things to note is that the Firebase Cloud Function option is not really viable, only because most of the time it's okay. Every 5 or 6 tries, it takes seconds to tens of seconds to work. I've also seen this with other projects using Lambda and other serverless things. Just cold start times on servers you don't have access to will kill you. The other really interesting thing is the fact that it is actually quicker if the server that is running the reducer is on the open internet on Heroku than on the same local wireless network that everything else is on, which is really counterintuitive. But I've noticed this with other projects, like another live demo we might or might not have time for, which is fine. Sort of for all this doesn't answer the question of whether this is fast enough. This sort of sets the stage for, all right, I now know that the way to test this would be with the reducer running on Heroku, and that will be the baseline for, is this actually fast enough for this to be a viable game or not? And if the answer is yes, awesome, great. If the answer is not, well, then the question becomes, does it seem like there are low-hanging fruit optimizations to get it fast enough, or am I better off solving this through design? Like in the case of this game, I could very easily shift it so that maybe just you're not allowed to be in the same room as someone else. So now I don't care about getting this immediate feedback of as soon as someone plays something, within tens of milliseconds you can see it, to, well, if it takes 200 milliseconds for you to get the latest data, maybe when you change rooms to a room where someone else just was, maybe like that animation takes 200 milliseconds to mask that. That would also open us up to other really common like netcode optimizations, both for games and for online real-time collaboration, where you could have almost a mutex lock based on physical space, where if I own this part of the game map, no one else can edit that until like I release my hold on it and I have made my changes to that state. Which again comes back to this larger point about designing for constraints. Like saying I want to make this word game, React seems like a really good fit for it. For certain levels of network latency concerns, there's a lot of really, really great things that we can get away with using Redux and giving us a lot of the benefits of Flux architecture for free. I didn't even talk about things like testing or playing back old game sessions that like, this is all phenomenal and super easy and things you'd have to spend lots and lots of time building in other game stacks that we get for free because we have the benefit of all of these open source communities building wonderful web tools to build business productivity apps, and we can use that to make weird experimental games. And when that stuff is in alignment, awesome. But again, there's the possibility that part of your design goes against the grain of that tooling. Whoa. Hey. And like, you have a choice. You can go against the grain of your tooling, and you can spend your time thinking with your engineering brain, how do we solve these hard problems? And that is interesting and fun. But it can also often be more fruitful and more fun to think about, well, what does it mean to go with the grain of the tooling? How can we make this game more React-y in a way that makes it useful? I don't think I have time for this demo. What I might do is, this is a game that like 50 people can play at once, if not more. So we might see if, okay. All right. I'll breeze through to the end of this and then we'll see. I might just leave it on anyway, because it might take a few minutes to get set up. Yeah, so but a high level, like that would just be another example of, here are other ways that we can work with this framework of using a React device as a controller doing button inputs for a twitchy action game, which still comes back to these things that are thinking about how to make games with React, I think is better approached as a design problem than a technical one. Which I hope is really interesting food for thought if you sit down and want to spend side project time working on a game and want to use the tools you already know rather than learning something new. And selfishly, I want to see more people doing cool stuff with React and web tech, both because I want to see more stuff like that, and maybe that means we'll get better tooling that's focused on games needs. And that's all I've got until I set up this game, hopefully. Let's see. 11? Nope. In theory, if you go to that website, this should work. Let me refresh that then. I have no idea whether this will be better connected over the venue Wi-Fi or LTE. That'll be an interesting experiment. No, I think this is not going to work. I tried this outside because I'm connected via my phone, and
you're going to have a hard time getting any LTE down here.
Yeah, I think that is the problem.
Are you not on the Wi-Fi?
I did not try it on the Wi-Fi. I will try connecting now. This is the thing that I'm worried about, where performance will then be heavily dependent on the specific properties of how the Wi-Fi router in this space is configured. So we can find out, and maybe I can talk about why it's not working.
Join red team.
Hey, someone's flapping around. Great. Awesome. So this is if you ever played the old arcade game Joust. It is like that. You're trying to sort of bop people on the other team on the head.
Oh, they're teams now. Sorry. I'm excited. What do I do? What am I?
It's Joust.
But yeah, so with this many people, it is very difficult to find yourself. But conceptually, if you run into someone on the other team, whoever is vertically higher wins. The goal of this game is to collect that ball and get it through your team's goal, but it's very heavy. So the bigger you are, the easier it is to move. You get bigger by killing people on the other team. With this many people, it can be very difficult to figure out who you are. Oh no!
I got disconnected.
Yeah, I think we overloaded the Wi-Fi in terms of it not knowing what to do with this many, like, small, tiny, flap WebSocket packets.
It's impressive that it lasted 3 minutes.
Yeah, that's impressive.
Better than Battlefield.
All right, that was a very janky demo. Thank you.